John, congratulations for the AS and Gibbs award. Today, I'm going to talk about fundamentals and predictions of cross phenomena. My name is Zi-Kui from Pennsylvania State University. Cross phenomena is about internal response of a system to external stimuli. For example, electric charge responds to temperature, mechanical stress, and the magnetic field. We get a range of properties of the system. Diffusion, with respect to heat conduction, is called Soret effect, is thermal diffusion. Or electric conduction, with respect to heat conduction, is Seebeck coefficient, thermoelectricity. So I'm going to mention a few of them in my presentation, particularly the diffusion, because that's John's field. So let's go back to the combined law of thermodynamics. And the equation here is from Mazahira's book. It's the combined law of thermodynamics in terms of internal energy. As you can see that you have the internal energy equal to the temperature times the entropy, pressure times volume change, and the chemical potential. And the last term here is the driving force. So that's very important because we talk about the internal systems. So we present the internal the processes. Okay. So when this term equals 0, that means the system is equilibrium. Now we see the pairs together, so we'll put the y and x representing these pairs. We call them conjugated pairs because they change the same direction in a stable system. So that means the dy to dx is positive, which is the second derivative of the internal energy to the molar quantity, Xa. Now, for non-conjugated pairs, that means now the y and the x are not pairs. For example, temperature and volume, and temperature chemical potential. So this is what we call cross phenomena. So it's one effect affects another property. So let's talk about conjugated variables, Ya, Xa, they're together. So this is actually, we have a famous Le Chatelier principle to describe this phenomenon. So what it means is that if you change the x of the system by a very small amount from outside, and the system will respond to that change. And the figure is from Mazahira's publication in 1995. So if you add heat into the system, for example, temperature is going to increase. So the change of the Ya is equal to derivative times the delta x change. And the Xi means here, Xi here means Xi is fixed here, means that it's frozen condition. That means there's no reaction in the system yet. No internal process in the system yet. Then the temperature of the Ya will jump up here. And now after that, the system has time to react to it. Also, you can have internal processes. That's called the Le Chatelier's modification. So it will bring the Ya down to another value. So this value is the same value as if you add the change, if you make the change very, very slowly at equilibrium condition. Okay. So during this process, all other XP molar quantities are kept fixed. Okay. So this is Le Chatelier principle. It works very nice. But however, there's one case in the literature I discussed for years, is for ammonia reaction. Okay. So what it means is that you have nitrogen plus hydrogen forms ammonia. So if you add nitrogen in the system, you would think that the reaction will go to right, produce more ammonia. So the fraction of N2 will decrease. So that's true. For example, so this is the question about reaction. So it represents equilibrium. So we start with the equilibrium system on this point. Now, if you add a very small amount of nitrogen, which is a nitrogen molecule, you can either add it or remove it. The system will come back. Or we'll not come back. We'll move to the equilibrium condition. Okay. So in this case, the fraction of the N2 nitrogen gas will either decrease or increase, depends on whether you add or remove nitrogen from the system. So that works nicely. However, if you add more nitrogen into it, okay? For example, if you add to this side, now you find that there's not an equilibrium state here. What happens is that if you make the finite disturbance, go to the regions 3 and 4, then you find the system will not go back to that equilibrium. It will find another equilibrium state. Okay. So now you see that if in this first region 4, if you add nitrogen, it will decrease, right? That's fine. So we're in that place, equilibrium state. But however, in region 3, okay, if you add nitrogen from here, 0.2 to 0.6%, or actually about 0.5%, the more N2 will be produced to its equilibrium state. So that's a violation of the Leclerc principle. So now you see there must be two conditions for the Leclerc principle to be violated. First, you have to get a finite disturbance. You have to go large change of the system. And that large change has to bring a system to a new equilibrium state. Okay, so this one here. So that looks also good. Now, this is for the variables, the conjugate variables, right? Now we talk about the non-conjugate variables. That's cross phenomena. What it means is that if you change one gradient, it will drive the flux of another molar quantity. Okay. So again, as you would imagine, that John did the work, worked on this topic too. So that's back in 2010. And John and Lars had publication and simulation of a carbon diffusion in steel driven by temperature gradient. Now we know that, right? Because the steel pipes, okay, you can have different temperature range outside and inside, you can drive carbon diffusion. So it's a very practical problem. Okay, in that one, you will say now you see the temperature drives diffusion, temperature gradient drives diffusion of a carbon, and then diffusivity. Again, that's John made a huge contribution in this field. I'm going to have a few slides to talk about that. The diffusivity must be a function of temperature and composition. Okay, so back in 1992, as you know that before that, in John's PhD thesis, he developed a digital software for simulation of diffusion. And in 1992 was a very nice paper talking about the models for numerical treatment of multi-component diffusion. And John studied the flux in that paper. They started John and I think it's Anders started flux in the lattice fixed frame of reference. Not because of diffusion, you have about a frame of reference. So lattice fixed frame of reference. That means you're sitting in the lattice and you see how it moves. And John wrote that equation. It's a flux of K is proportional to its own chemical potential, nothing else. It is not in any other chemical potential of other elements. It's to its own chemical potential gradient. That's very important. Of course, because substitution and the individual diffuse differently, so the equation is a little bit different, just about the fraction of the vacancy for interstitial diffusion. For the substitute diffusion, the y is inside omega, as you see here. All right, now, but of course, when you experiments, you are outside. So you see, you have another frame of reference, which is volume fixed frame of reference. In this case, you have to change the frame of reference. Now you see this is only chemical potential of the diffusion species, but when you change the frame of reference, what happens is that chemical potential of that component is related to other ones now, right? The diffusion, okay? So now you see that the diffusion now have the flux in this frame of reference has the chemical potential gradient of all species. Okay, so in relation, you get a different kinetic coefficient now between the one frame of reference and another frame of reference. Okay, but this one is diagonal because off diagonal terms are zero. But for the new frame in the new frame of reference, the error parameter is not diagonal anymore. So now we know that we need to do the concentration, right? Okay, we need concentration. So we need to change the chemical potential to the concentration gradient, chemical potential gradient to the concentration gradient. Of course, we know how to do that, right? We get some thermodynamic factor. But again, the chemical potential of one element is a function of all compositions. Okay, so then now you can do that, do the thermodynamic factor, then you can recombine it and it changes the order of the summation. You define a new diffusivity. Okay, we call it chemical diffusivity now. Now, because in most of the cases, you have all the composition addition summation equal to 1, so you make it a dependent one. Okay, you independently driving forces for the concentration gradient. So you now going to reduce the chemical diffusivity. This is the interdiffusion coefficient we typically call it. Now, if you put them together, all the Young's fantastic work. Now we have a mobility, right? We talked about M before. And M can also be related to the tracer diffusivity, so the Einstein equation. And then we can change the M mobility to the L coefficient. Then we change the frame of reference. We change it from the chemical potential gradient to the concentration gradient. We get an independent self-driving force. Okay. So this is what we measure experimentally. Now you can see, you can go backwards, you get this chemical atomic mobility. That's what is stored in the dictionary database, mobility database. However, we can also change directly from this one to the concentration gradient instead of going to change the frame of reference. If you do that one, you will get another diffusivity. We call it intrinsic diffusivity. Again, you change the independent set of driving forces, then you get a reduced intrinsic diffusion coefficient. Now, it's important to see that for all of these, you can see that they have error contribution and also thermodynamic factor. So the diffusivity we typically talk about is not only kinetical properties. It's the combination of the kinetical properties and the thermodynamic properties, with the phi represents the thermodynamic factor, secondary derivatives of the Gibbs energy, or the Helmholtz energy, depending on the system. But in our experiment, it's Gibbs energy here. So that's very important, right? We know that for unstable systems, binodal, this becomes negative. Okay, that's why the concentration, the diffusivity becomes negative in the unstable region. All right, so now let's talk about the cost effect, temperature gradient. Again, go back to Young's paper I mentioned earlier. So in the last fixed frame of reference, again, this is all the off-diagonal terms are 0. Okay, so this one's actually only one term. It's the chemical potential of the K only. Okay, so only LKK. And then you have another term in John's paper. You wrote the LKD, temperature gradient, and then define the LKD like this function: is the LKK times QK star. And the QK star for the carbon, it is like the chemical potential to the concentration. The U fraction is the special concentration. Then concentration to the temperature is actually the chemical potential to temperature derivative. Okay. Now the question here is right. Think about this one. So we put when the concentration when the off-diagonal terms is 0, why this one? Why don't you get this one equal 0 too? That's actually the question, right? So we can talk about that a little bit later. This maybe should be 0 to start with, but then of course we have the cross term. We'll talk about that later too. Okay, so this is the last fixed frame of reference. Then you can turn to volume or number fixed frame of reference. You get a JK prime. Now you got the term now. You must have a temperature gradient now. This chemical potential is function of temperature gradient, function of temperature. So you got this L prime here divided by T square, which has mobility. Let's go to LKK. And the Q star, which is from this derivatives, from this derivative. Okay. Now what do you need? You need the Q star, right? Mobility is already known. So you can do simulation. So in that paper I mentioned, in John's paper with Large, and they simulated one. So you first have to decide what the Q star value. So in that experiment, people assume you reach a steady state, they evaluate the Q star. What does it mean by the steady state? There's no diffusion of carbon anymore. Flux of carbon is 0 everywhere. Okay, that's the steady state. So you can evaluate Q star. And from the experimental data points, you can see that after 100 hours, you find that profile measured. Okay. However, and also temperature profile. So the dashed line is temperature profile. Now you see that simulation does not match experiment. But also you can see that another point is that you see that actually there should be still continued diffusion because the diffusion is not reached the steady state yet. So what does it mean? That means that actually after 100 hours, the diffusion is not a steady state yet. So, and then that means the Q star value is incorrect. So then in Young's paper, they evaluate this Q star, you have to match the experiment. They found the Q star should be minus 44 instead of minus 12. Q star should be larger. Okay. So now it means that now with that new Q star, they simulate this one, match the experiment very well. And then the question is that how long time it takes to get a steady state, right? Turns out I think it should take about 3,000 hours. 3,000 hours, that's a pretty long time. So now you see that after time can be infinite, you feel that the profile looks like this. Right? It's very smooth now. No, this value anymore. Okay. So now it reaches steady state. All right. So it's very nice, very beautiful work. Now let's go back to Q star. Q star is a very important parameter, right? Very important parameter. Okay. So let's go back to even one step further. It's the Onsager reciprocal relations. What it means is that for a change of flux of anything, the molar quantity in the system, based on Onsager relation, it means that Onsager equation, it means that it should be minus the gradient of all driving forces. Okay. And then Onsager relation says that this matrix, this L matrix, is symmetric. But we all know that symmetric matrix can be made diagonal. Okay. So of course that people will think about this one. So people work on that. There's one paper, it's a lot of work in this field to try to understand this cross term. Okay. So it's very interesting work published in last several years by Kochinsky and Gurubella. They talk about some diffusion. That means diffusion due to temperature gradient. They derive some equation, shows that, okay, for diffusion, you derive this equation, shows the diffusion is only the function of temperature, the chemical potential gradient of that species alone. And that means that all the off-diagonal terms are zero. So what is that? What does this really mean, right? What does this mean? That means, let's look at the Soret coefficient. What it means is that the chemical potential is a function of temperature, pressure, composition, and other field, magnetic electric field, right? So if you do that one, think about the gradient of chemical potential. Of course, then it will be a gradient of chemical potential will be gradient of with function of temperature, gradient of pressure, gradient of all the compositions, and the gradient of the other fields, right? Okay. Now, if you put it back to the Fox equation, you put the Fox equation, what do you see? That, okay, this is partial entropy, partial molar volume, thermodynamic factor, this is another partial quantity we have here. Okay, so what it means is that the Soret coefficient is actually just the partial entropy. Let's go back to the equation in John's work. The QC, that's basically the Soret effect, is actually the chemical potential carbon to temperature gradient. That's chemical potential carbon to temperature gradient. So that should be related to partial entropy of carbon. Okay, so that will not resolve yet. So I made some comment about their work. Okay, because they have some problems with the derivatives. So I tried to show that what the proper derivatives should be. So now let's put them together. So it's really the derivatives we should really think about, right? First is between x and y. X is the molar quantity, as shown here, and the y are the potentials. So these are the typical physical quantities we're talking about. Okay, the diagonal terms are the conjugate variables. between conjugate variables, they're always positive for stable system. But however, the off-diagonal terms here, they're not conjugate, they're between non-conjugate variables. They can be positive or negative. For example, we worked on the negative sum expansion. We have a few papers, this is put in my overview paper. So all the quantities of the off-diagonal quantity could be negative. And if it could be positive or negative, then it could be zero, right? Okay. And then positive and negative could be infinite and divergence. So it's all kinds of properties we can study. Now, the cross phenomenon is between different variables, not conjugates, right? It's between the potentials, actually. Okay, that means the potential for one potential will drive the flux of another molar quantity through the change of its potential, conjugated potential. So now we get a new set of data. So it's potential here, it's also potential. Potential to potential derivative, of course, the data is one, but off diagonal is all the cross phenomena we're talking about. So it's a lot of problems we can study in terms of the derivatives. Okay. So one of them we did recently, it's a Seebeck coefficient. I mentioned the Seebeck coefficient before. It's a temperature driving electron conduction. Okay, it's electric conduction by temperature gradient. So we can calculate Seebeck coefficient now. Okay, Seebeck coefficient could be negative or positive. Okay, because off diagonal terms. So it's actually for p type and n type, they have different sign. N type is negative, p type is positive. So it's one example for length of entire line. Okay, this is all negative because n type. But if you take another materials, you can change the different n type to p type by doping. You will change Seebeck coefficient, change the sign. Okay, to summarize, I talk about mainly transport cross phenomenon. Okay, so it's the gradient of a potential, which is temperature, magnetic field, electric field, or elastic field, drives diffusion. Okay, through the effect on the chemical potential of that species. So we'll talk about the thermal transport. Okay, it's the mass transport and electron transport. We talk about cross diffusion, up here diffusion, for example, exactly with up here diffusion is why it happens because it's this change of the chemical potential between two elements. We talk about the transport due to the stress, transport due to the electric field, magnetic field. Of course, this is all about transport cross phenomenon, right? We can talk about a lot of other phenomena, non-transport cross phenomenon. We can explore. Basically, the derivative of the two potentials is related to the derivatives of their corresponding molar quantities. With that one, I want to thank you for your attention. Again, congratulations to John for receiving the ASM Gibbs Award. Thank you.